This Quicklearn Bullet introduces bootstrapping, a technique for deriving from the ordinary yield curve implied zero coupon rates and discount factors for each maturity. Consider a bond market that has only 3 securities outstanding with the following characteristics. A 1-year discount security priced at 95 and maturing at par. A 2-year note priced at par and paying an annual coupon of 8%, and a 3-year note also priced at par and paying an annual coupon of 9.5%. Now suppose you wish to determine what would be the yield on a 2-year zero coupon bond, which does not exist in this market. Remembering that any bond has a price equal to the sum of its discounted cash flows, you write this equation for the 2-year note, where df1 and df2 are the discount factors for the cash flows occurring under this note at the end of year 1 and year 2 respectively. Note, as usual, the inclusion in the final cash flow of the principal as well as the final coupon. But you know that df1 is 0.95, since the 1-year note represents the right to a $100 cash flow in 1 year and is priced at 95. And so you can solve the above equation for df2, which now has only one remaining unknown. Rearranging the above equation gives df2 equals this amount here, which becomes 0.8556. Furthermore, df2 being the discount factor for a cash flow occurring at the end of 2 years equals 1 over 1 plus the zero coupon rate for 2 years squared, and therefore solving the equation enables us to write z2 or z2 is the square root of 1 over 0.8556 minus 1, which becomes 8.1125%. And more generally, from any discount factor, we can derive the corresponding zero coupon rate, and from any zero coupon rate, we can derive the corresponding discount factor, writing very generally dfn equals 1 over 1 plus zn to the n, where zn means the zero coupon rate for a tenor of n years. To derive the 3-year zero coupon rate and discount factor, we proceed as before and write the fundamental pricing equation for the 3-year note as price equals cash flows individually discounted, which enables us to solve for df3 since we already know df1 and df2. This leads to df3 equals this quantity here, and therefore df3 is 0.7566, and since df3 is 1 over 1 plus z3 to the power 3, it follows that z3 is 9.7435%. Most generally, assuming we have already calculated df1, df2, all the way to dfn-1, and now wish to calculate dfn from the note maturing in n years and carrying an annual coupon of c suffix n, we would write for this note price equals cash flows individually discounted at separate discount factors. Rearranging the equation above enables us to write this here, which after a little algebra gives us dfn solely derived from the price and coupon of the n-year bond, as you can see, and the discount factors previously calculated. Now we consider the more realistic case involving securities shorter than 1 year and coupons that are paid more frequently than annually. Suppose the notes currently outstanding in the market have the following terms as of June 30, 2009. Take note, first, of 3-month and 6-month bills with a face value of 100 but a price below 100 and no coupon. i.e. discount securities which provide all their yield in the form of this discount. Then a 1-year note issued March 30, 2009, maturing March 30, 2010, and paying 9% quarterly. And then again a 1-year note issued June 30, 2009, i.e. today, maturing June 30, 2010, but with an 8% quarterly coupon. So reflecting presumably some drop in rates that happened in the last 3 months. Note in particular that since the 1-year note is issued quarterly, the instrument in the third row that was issued in March 2009 now has only 9 months left, only until maturity, and therefore only 3 coupons remaining. For this note, we can write the normal relationship between its price of 100.8 and its cash flows, representing quarterly coupons of $2.25 each, discounted appropriately by the right discount factors. DF 0.25 here refers to the discount factor for a cash flow occurring 1/4 of a year from the measurement date, and so on for the other DFs. And of course, please note the inclusion of the principal as well as the last coupon on the last date. But we know from the discount securities that DF 1/4 is 0.98 and DF 1/2 is 0.96, which enable us to write for DF 0.75 this quantity here that calculates out to 0.9431. And in turn, this leads to the 1-year note issued on June 30, 2009, maturing on June 30, 2010, which appears in the bottom row, for which we can write its price equals the discounted PV of its $2 coupons and $100 principal at maturity as before. And this finally leads to this quantity here, leading to DF1 equals 0.9250. Before concluding this video, we compare par and zero coupon curves under the following 3 scenarios: when the par curve is upward sloping, when it is flat, and when it is inverted. Starting with the scenario in which the par curve is upward sloping, you will notice in the graph appearing now that for every maturity beyond 1 year, the zero coupon rate is slightly higher than the par rate. At first sight, it may seem that the gap between the two is increasing as we go further out along the curve, but closer observation reveals that this gap eventually peaks and then starts decreasing a little. Now we take a par curve that is flat, run the calculation again for the zero coupon rates, and discover, as you see in the graph appearing now, that the par and zero coupon curves now lie exactly at the same height as each other for all maturities. Finally, we address the case in which the par curve is inverted. The graph appearing now reveals that the zero coupon curve lies underneath the par curve for all maturities past 1 year, and that gap between the two curves expands the further out we go. This completes this quick learn bullet on bootstrapping techniques, on discount factors, and on zero coupon rates.